It is the 21st century. The human population is growing. Industrialization has reached immense levels and human development is exponential. Our energy consumption has reached unprecedented levels. Our reliance on fossil fuels for energy has created a multitude of problems that put our planet at risk. Climate change, rising sea levels, and increased freak weather. Scientists and engineers from across the globe have spent decades trying to devise a solution for this reliance on fossil fuels. Wind power could be the answer. A team of aeronautical engineering students from Imperial College London were commissioned to design, manufacture, and test their own small wind turbine. This specifically included a biologically inspired feature to help create new alternative designs that could be applicable in the future of this industry.
The turbine had to meet a set of requirements. It had to be a horizontal axis design, rotate clockwise when viewed from the wind direction, and its angular velocity could not exceed 3000 rpm. Also, the maximum CP had to be at a maximum tip speed ratio, defined as the ratio between the blade tip speed to wind speed, of between 3 and 8. The maximum weight for the design was 200 grams, and the design should fit as a single piece in a 3D printer of dimensions 400 by 100 by 150 millimeters.
The first stage of the design involved the aerodynamic optimization of the blade. Using actuated disc theory, the power extracted by a turbine is related to the area of the turbine and the induction factor across the turbine. We had to maximise CP, which would theoretically be the best limit, but this is not possible for small turbines. To begin, we selected a radius that could be printed without a hinge mechanism so that it would be easy to manufacture and meet the weight limit. Smaller radius also meant blockage would have less effect, and the correction is not usually necessary for less than 5% of the tunnel area. As an objective was to accurately predict the optimal TSR, minimising blockage effects would make this easier. The blade is most efficient when the circulation around the blade is constant. To achieve this, we varied the chord along the blade. We calculated the twist angle using the local velocity and circumferential velocity at points along the blade, so that the airfoil will be at the optimum angle of attack.
We applied twist to the blade to keep the angle of attack constant at the value that would optimize CL over CD for our chosen airfoil, based on graphs from the airfoil database, in order to maximize rotor torque. The airspeed felt by the blade is a resultant of both the incoming flow speed and the speed of the rotating blade. Taking this into account, the angle of attack and the required twist was then calculated.
Using this, we then used Q-blade simulations to find the best TSR, and then used a MATLAB script to find the blade properties. When designing the nose cone, we were inspired by the HAWT series shapes, which minimise drag. We opted for a more rounded nose cone that will reduce weight.
When choosing our airfoil, our aim was to maximise the rotor torque, as this would make the blade more efficient, and this meant maximising the lift-to-drag ratio. We searched an airfoil database for suitable airfoils and considered airfoils in the NREL, SG and NACA airfoil series. We eventually decided on the SG 6043 as it had a high lift-to-drag ratio and its section was sufficiently thick to withstand structural loads.
However, aerodynamic efficiency is worthless without structural integrity. Therefore, after the aerodynamic optimization process was completed, the structure's robustness was then analyzed.
Although large turbines tend to have higher efficiency, we went for a small unibody design for two reasons. Firstly, we needed to accurately predict the TSR at maximum efficiency. If we make the turbine big, blockage effect in wind tunnel will introduce great discrepancy to efficiency, which would lead to inaccurate prediction of TSR max. Secondly, large blade design requires a hinge at a cone in order to fulfill the 3D printer's dimension requirements. As a hinge and extra gluing will affect the integrity of our structure, we decided to choose a small blade design.
Blade element momentum theory analyzes the way in which a wind turbine functions by finding a momentum balance on an annular stream tube going through the turbine and by observing the loads acting on the blades due to the lift and drag coefficients. The blade element theory makes use of two assumptions. A. The forces of the blade elements are induced exclusively by the lift and drag coefficients, and B. The blade elements experience no aerodynamic interactions between them. This theory requires that the blade has to be divided up into sections and the flow be calculated individually for each section. The overall results are obtained through integration along the blade span. The moment of inertia is calculated by integrating all the contributions due to infinitesimal rectangular sections of the airfoil. A neutral surface position was fixed for the inertia of each section. Following observation, it was found that the inertia is proportional to the formula displayed. Once the moment of inertia was computed, the angular deformations and the deflections were then obtained using the following equations. The bending moments and the deflections of the blades were computed in MATLAB. The deflections obtained were acceptable as they were small enough to not cause damage to the wind turbine.
Finally, we added tubercles to our design. Tubercles are large pumps that are inspired by wheels. They work by channeling the flow and increasing its velocity over the airfoil. This reduces the parasitic drag at the wingtip of the blade and makes the whole turbine more aerodynamically efficient.
The turbine was manufactured in two stages. Firstly, the hub was produced from a circular cylinder of aluminium. CNC turning was used to drill a hole here. 4-axis machining was used to mill the outer hexagonal shape of the hub. Parting was then used to cut the hub to the required length. The second stage involved the 3D printing of the design. 3D printing is a manufacturing additive process which is done under computer control. It involves the addition and solidification of several layers of the material to create a part.
The printing process had a great influence on how the wind turbine turned out. The turbine was designed in such a way that, when printing, the layers would be added in the direction parallel to the direction of loading, which increased the strength of the part and ensured it would not break during testing. Although this positioning didn't benefit the aerodynamics of the turbine, we decided to prioritize structural integrity over a smoother finish of the surface, which could ultimately be achieved through sanding as well. Moreover, as 3D printing is not an entirely foolproof process, the wind turbine was found to have a number of defects. As you can see, we had stepping trailing edge, rough leading edge, and missing material at several spots. To reduce the impact of printing imperfection, we added epoxy to dents and sanded the blades to obtain a smoother surface and thus reduce skin friction.
The turbine was placed in a testing rig and tested at various flow speeds in a wind tunnel. Brakes were then applied and the turbine was slowed down to measure the generated power output. The turbine was not able to self-start at 6 meters per second. This was probably due to the cone being overweight in relation to the blades. Hence, only the data at 8, 10, and 12 meters per second was recorded. Some fluctuation was found in the data due to the interference between the wakes of the two blades. After data processing, it was found that although the turbine was expected to produce a maximum power output of around 0.45 at 12 meters per second, the maximum CP was recorded to be 0.12. As the results did not meet our expectations, to study the effectiveness of our bio-inspired feature, we removed the tubercles and did another test. The maximum efficiency was found to be around 0.1639. This is about a 33% rise. This suggests that the tubercles were not properly designed. However, the predicted TSR was indeed more accurate with the tubercles on.
Having reviewed the performance of our turbine, there are a few improvements we could have made. Firstly, improvements could have been made with the cone. In hindsight, we made it a bit too heavy and robust, and weight could have been saved by reducing its size. We also could have tried designs with the tubercles at different locations along the blade. They could have had a better effect near the hub, for example. This wasn't feasible to do during our original design process, as we couldn't model the tubercles in Q-Blade, and we could also only print and test our turbine once.
Although we didn't produce our desired power output, overall the project was a success. We met all the requirements and our TSR was well within reasonable distance from our prediction. Further research should now be conducted on the location of the tubercles on the blade. Despite tubercles still being a fairly primitive technology, they definitely are promising in the wind energy industry.
We're inside a wind tunnel.